Hello everybody, and welcome to my 24th video. This is on a quaternary algebra with 3 binary operators. And this algebra doesn't use any 2-valued unary operators, it only uses 3-valued unary operators. So here we have the unary operators, unary meaning one input. This is A plus, which is A plus 1 modulo 4. This is A plus plus, which is A plus 2 modulo 4. And this is A minus, which is A plus 3 modulo 4. So here we have the truth tables. This is A, 0, 1, 2, 3. A plus, 1, 2, 3, 0. A plus plus, 2, 3, 0, 1. A minus, 3, 0, 1, 2. These are the binary operators. These are two of the binary operators. Binary in the sense that they require at least 2 inputs. So here's the minimal function, 2 inputs A and B, and this is the output A and B, or A min B. For example, 1 and 3, the minimum value of 1 and 3 is 1, so A and B equals 1. So meaning the maximum function, 2 inputs A, B, maximum value of 2 and 1 is 2, so it's there. A plus B equals 2, A max B. This is the ampersand function. It's a 2-input function only. I've labelled it X and Y, these are the inputs. This is X ampersand Y, so this is the output, and I've split it up into 4 tables, A, B, C and D. Now this function is non-commutative, which means that X ampersand Y isn't the same as Y ampersand X. For example, Y equals 0 and X equals 1 equals 1. But Y equals 1 and X equals 0 equals 2. So it's non-commutative. It matters the input, which input you assign to each input matters. So, like I say, I've split it up into 4 tables. From table A, X can assume the value of 0 or 1, and Y can assume the value of 2 or 3. If X and Y is a don't care state, which can assume the value 0, 1, 2 or 3, X and Y are R's. The value of R in X is 0, 1. The value of R in Y can be equal to 2 or 3. Similarly for input B, table B, X assumes the value of 2 or 3, Y assumes the value of 0 or 1. X and Y 0, 1, 2 and 3 for these input combinations. If X equals 0, 1, 2 or 3, X and Y are R's, redundant states, which R can assume the value of 2 or 3, or R can have value of 1 or 0 in there. So for table C, X assumes the value of 0, 1, Y assumes the value of 0, 1. Again, if X ampersand Y is X, then R, X and Y are both R's. X assumes the value of 0, 1, 2 or 3 there. R assumes the value of 0, 1 there and 0, 1 there. For table D, we have X and Y equals 0, 1, 2, 3 or X here. X can assume the value of 2 or 3, and Y can assume the value of 2 or 3. So this X can assume the value of 0, 1, 2 or 3 there. R assumes the value of 3 or 2, and R there assumes the value of 3 or 2. Right. Here are some algebraic rules. These are with reference to the maximum and minimum functions. So rule number 1, A min A plus min A minus equals 0. A max A plus max A minus equals 3. A min 3 equals A max 0 equals A min A equals A, and A max A equals A. So we have factorisation. A min B max A min C equals A min B max C. That's a sum of products expression, and A max B min A max C equals A max B min C. That's a product of sums expression. Right. Here we have an example from, this is table A, which I showed you for the ampersand function. I've chose an arbitrary function f for inputs A and B, and I'm using the coding, this coding here for f and x and y for the ampersand function. So for example, f equals 3, y equals 3 and x equals 1, f equals 3, y equals 3 and x equals 1. I have included some don't care states from f. Where that happens, y and x are equal to redundant states. Here r represents the value of 0, 1, or r there for 3 or 2. Right. These are the counter maps for example 1. This is input x for the ampersand function. Basically this counter map is two-valued. You do that by adding a constant logic state to the expression of x. In this case it's a quaternary logic 1. This is input A, this is input B. These are the coordinates of the counter maps for A and B. So this coordinate is a 1 at A equals 1 and B equals 1. You get the Unary operators by saying to yourself, what do I have to do to a 0 to get it to you're using the loop in the zeros, so you say what do I have to do to each number to get it to a 0. So for A is a 0, you don't have to do anything to 0, so it's A. You have to minus 1 from 1 to get to 0, so it's A minus. You have to add 2 to 2 to get it to 0, modulo 4, so it's A plus plus. And you have to add 1 to 3 to get it to 0, modulo 4, so it's A plus. Same for B. So you loop in the zeros. So here you loop in powers of 4. So 4 to the 0 is 1, or 4, or 16, or however many is the power of 4. So here I'm looping an entire column, and I've called it A plus because I've looped the entire column, and here I've looped the entire row, and that's B plus. So here I haven't been able to loop an entire row and column, they're just single values. So this coordinate here is A minus or B, A minus there, B there. This is A plus plus max B minus, A plus plus max B minus, A max B plus plus, A max B plus plus. So you connect them all these terms together with the minimum function, and you get an expression for the function x. So that's A plus min B plus min A plus max B plus plus min A minus max B min A plus plus max B minus min 1. Quaternary logic 1. Right, that's for example, that's for function x. For the function y, you're looping the 3's. So you have to say to yourself, what do I have to do to each coordinate of the counter map to get it to a 3? Well, you have to minus or add 3 to 0 to get it to a 3, so it's A minus. You have to add 2 to 1 to get it to 3, so it's A plus plus. You have to add 1 to 2 to get it to 3, so it's A plus. and 3 you don't have to do anything, so that's just A. Same for input B, so input A, input B. So this coordinate of the counter map is a 3, A equals 1 and B equals 1. So here are the expressions which I've looped. I've looped the entire columns here. This is equivalent to A, this is equivalent to A plus, and these coordinates here are A plus min B plus plus. Have I got that right? Yeah, A plus plus min B plus plus, and A plus plus min B plus. So you can all these expressions together by the maximum function, and you add a constant logic state to the expression to make it two-valued. And this constant in this case is a quaternary logic 2. So this is a product of sums expression, and this is a sum of products expression. So finally, the function f, which you saw in the truth table, is x ampersand y. This is a function x, this is the function y. Now I'm just going to quickly go through the algebraic minimization for the function I've just shown you, example 1. So this is for the function x. So this is the expression for the zeros, all single coordinates in the counter map. I've labelled each expression and the r's, the don't care states. You can choose to loop the r's in the counter map or not, it doesn't make any difference, you use it to your advantage. I've used this one here. So this is function x. I've used those 4 functions there, 2 there, 10 there, 5 there, 9 there, and similar for this one, it's continued, 6 there, where's 6 there, 7, 8 and 9. I've used 1 there, 3 there and 4 there. So I haven't used this redundant state here. So what do? Well, I can factorise the A plus there and collect the B terms there. So this is A plus max B min B minus min B plus plus min B plus. And I can factorise the B plus terms here. So this is A min B minus min A plus plus min A plus max B. Then I've continued that down there, adding the constant 1 logic state in. So this is equal to 0, this is equal to 0, so that's A plus plus max 0, min 0 max B plus, then the rest is copied there. So A plus max 0 equals A plus, B plus max 0 equals B plus, and I've copied down the expression there. So we've got x equals A plus min B plus max A minus plus min max B, min A plus plus max B minus min A max B plus plus min 1. Right, so this is for the function x. Now for the function y, looping the 3's, so there's the 3's, these are all the coordinates of the counter map where f equals 3. I've added a constant logic state to the expression, which is a quaternary logic 2. These are the r's, where the function equals x. The r states, a min b plus plus a plus min b plus max 2. So this is the expression I've used, 8 there, 6 there, 9 there, 2 there, 7 there, 10 there, 4 there, 1 there, 3 there and 5 there. So what can I do? Well, I can factorise the a's here and collect the b terms there, which I've done there, and I can collect the a plus terms there and collect the b terms, which I've done there, and I've just continued this down here. So, right, you can, this b term here, b max b plus max b plus plus max b minus equals 3. Same here, equals 3. And I've just copied the rest there. So a max 3 equals a plus max, sorry, a min 3 equals a plus min 3 equals a plus, and I've copied that the rest there. So the function y equals a plus max a plus y equals a max a plus min b plus max a plus min b plus max 2. So that's how you can do it algebraically. I wouldn't recommend you do this method. This is just to show how it works. But you know, the Cannon map is a much easier method of doing it. Right, I'm going to go on to example 2. This is table B for the ampersand function that I showed you. Here we have a two input function a and b, the same function f as in example 1 for table A, and I've coded y and x according to this table here. For example, f equals 3, y equals 1, and x equals 3. So there we go, f equals 3, y equals 1, and x equals 3. So this x assumes a value of 2 or 3, and r assumes a value of 2 or 3. Here y assumes a value of 0 or 1, and r assumes a value of 0 or 1, and x here assumes a value of 0, 1, 2 or 3. Right, so let's have a look at the Cannon maps. This is the Cannon map for function x, the function x. Here we're looping the 3's, so again, these are the coordinates of the Cannon map for A and B. So again, what do you have to do to 3 to get it to... What do you have to do with the variable to get it to 3? You have to add nothing, so it's A. Again, add 1 to 2, A plus, add 2 to 1, A plus plus, and add minusing 1 is the same as adding 3 modulo 4, so it's A minus. Same for B. So none of these coordinates can be looped in a group of 4, so they're all single coordinates. So here, this is a coordinate where a equals 2 and b equals 0. It's a plus min b minus. And similarly for all the rest of them. For example, this one is a plus plus min b plus. You just read off the coordinate from the Cannon map and assign the variable to it. So x equals a minus min b minus max a minus min b plus plus max a plus plus min b plus plus max a plus plus min b plus max a plus min b minus max 2. You're adding a constant logic state to expression to make it two-valued. In this case, these values of r, you can choose to loop them or not, but we didn't include them in this case because there was no advantage for it. For function y, so again, Cannon map, this is A and this is B. Again, you're looping the zeros, so what do I have to do to 0 to get to 0? Nothing, so it's A minus 1 to get it to 0, A minus, add 2, A plus plus, add 1, A plus. Same for B. So I've looped a group of row of 4 here, and that's A. And this is A minus and B plus, A minus and B plus, A minus and B plus there, A minus and B plus there. So the function for y is A min A minus max B min A minus max B plus min 1. Constant logic states the quaternary logic 1. So this is a sum of products expression x. This is a product of sums expression y. So the function f equals x ampersand y. Here we have example 3. This is for table C in the ampersand function that I showed you. Again, inputs A and B, two inputs, the same function f. For example, f equals x, x and y both equal r. Yes, there and there. And if f equals 1, y equals 0, x equals 1, f equals 1, y equals 0, x equals 1. So for this, x assumes a value of 0 or 1, and y assumes a value of 0 and 1 too. The r assumes a value of 0, 1, that assumes a value of 0, 1, and x assumes a value of 0, 1, 2 or 3. So these are the kernel maps for example 3. Here x, kernel map for x. You loop in the zeros, so again you assume, you say what you have to do to that number to get it to a 0 for all of these, and you assign the variables A and B. Here I'm looping an entire column here, so that's A plus there. Looping an entire row there, so that's B plus. And these single logic states, you can't loop them in a group of 4, so they remain single. So this coordinate is A plus plus, and that's B minus, A plus plus and B max, B minus. Similar one for this, A max B plus plus. This is A minus max B. So you connect all these terms together with the minimum function, and you get x equals A plus min B plus min A max B plus plus min A minus max B min A plus plus max B minus min 1, adding a constant logic state to the expression. For kernel map y, for the function y, again you're looping the zeros, so it's the same labelling of the variables. I'm looping a 4 column here, so that's A. This is A minus max B, and this is A minus max B plus. So the function y equals A minus A min B minus max B min A minus max B plus min 1. So you're adding a constant logic state to the expression to make it two-valued, and the function f equals x ampersand y. So lastly we have example 4, which is table D. Again, same function f, same input variables A and B and T, and table D. So there's a function f and a don't care state, which is going to assume the value of 0, 1, 2 or 3. X assumes the value of 2 or 3, and so does y. Value of r there is 2 or 3. The value of r there is 2 or 3. So for example, we have f equals 3, x, y equals 3 and x equals 3, f equals 3, y equals 3, x equals 3. So we'll see the kernel maps for x and y for table D. So this is the kernel map for x, using looping the 3's. So again, you say what I have to do to the coordinate of the kernel map to get it to a 3. Nothing in this case, so it's A, etc. Same for B. I haven't been able to loop any groups of 4. You have to loop in rows or columns. You can't go looping a square there, that's not allowed. It has to be a row, column or single variables, and then when you include a loop you have to loop entire loop of A or entire loop of B, or if it was a 3 variable, an entire loop of C. So here this is coordinate is when A equals 2 and B equals 0, and the variable A plus min B minus, this is A plus there, B minus there. Similar deal for the rest of them, and you connect them all together with the maximum function, all these terms here, So x equals a minus min b plus max a minus min b plus plus max a minus a plus plus max min b plus plus max a plus plus min b plus max a plus min b minus max 2, adding the constant logic state to the expression to make this two-valued. For a function y, again you're looping the 3's, so it's the same labelling as here. This is variable a, this is variable b, and here I'm looping an entire column here, so that's a, and then similarly entire column there, so that's a plus, that one a plus, and this is a plus plus min b plus plus, is a plus plus min b plus. So you connect all these terms together with the maximum function, and you get y equals a max a plus plus min b plus plus max a plus plus min b plus max 2, and f equals x and y. Right, I think that concludes the video. I'd just like to say I hope you've enjoyed it. Thanks for watching. Bye.